Thank you very much for the invitation, Tony. Really appreciate the opportunity to be here. I want to acknowledge, of course, my good friend Andrew. I believe we're probably the only two people from Australia, so Andrew and I have known each other for a long time. I want to, of course, acknowledge RAC with the CAM and the board for the opportunity to share with you a little bit of our journey at the SMaRT Centre at the University of New South Wales in Sydney. And I'll probably take a view that is a bigger picture view of what it means to be sustainable and what it means to actually really truly look at sustainability from the lens of the fact that we do need materials, we do need products, whether they are electronics, whether they are in our built environment, it doesn't matter. But we also at the same time need to be very mindful of the fact that right from get-go, when we design materials and we think about our feedstock and how we manufacture, we also have to think about what it means to have the whole of life cycle in our minds. Sustainability cannot be an afterthought. Sustainability and the way we respect our planet and we make sure that our planet is not going to be cause any harm from the kinds of materials that we know we are creating. A simple example could be different kinds of plastics. We know that there are so many different kinds of plastics that lead to the formation of microplastics. And of course, the challenges with simple materials like plastics that can be an interesting challenge for our communities. Now, there is lots of good work happening in this world, of course, in terms of looking at biodegradability. So you can start to look at those changes that are happening in our society. But what about all of those other complex products? We've heard a lot of conversation around batteries, for instance. Lots of materials, complex oxides and other materials that are all present inside batteries in what is called black mass. That black mass, whether you're talking about lithium-ion batteries, different technologies, nickel metal hydride batteries, they contain important elements that are present in different forms, whether it's cobalt, whether it's lithium, nickel, so on. How do you actually start to plan for not just recycling, thinking from the lens of recyclability, but taking that whole of life cycle and thinking all the way to manufacturing? So what we are really saying is recycling just from the lens of just collecting materials, having system to collect is not enough. What we need to be able to do is connect through the entire supply chain. And those are the kinds of thought processes that have gone into us developing various technologies. As SMaRT Center's technologies and microfactories, I'm going to give you a little bit of an overview today, has actually already shown that it is possible to be able to take those complex materials and, of course, go back and regenerate them so that we can actually provide these materials to be part of our supply chain. Why does it matter? Well, look at all those important metals like copper, like nickel, and of course a whole range of other materials like steel, aluminum, and of course the list goes on and on. Look at the amount of energy that it takes to manufacture those materials, from mining raw materials to purifying it, to be able to then manufacture products. All of that costs energy. Why would we not see our end-of-life materials as renewable materials? Because what they bring with it is basically all that embedded energy that has been put into making those materials in the first place. So the fact that you can actually start to think about decarbonization and lowering our carbon footprint of different kinds of materials, their manufacturing processes, is based on one simple question. Can we really bring all of those materials back to life over and over again? So of course, if you ask the question, what's a sustainable material? Well, a sustainable material is something that has already been made. If you've already made it, you've already put that energy into making it in the first instance, well, of course, you can bring it back to life over and over again, assuming you understand and you know how to remanufacture different kinds of products. And of course, that then comes to that important challenge. If we're talking about materials and products, fundamentally, if they have to be renewable for the sake of our planet, if they have to be renewable in terms of materials, going round and round and being able to be manufactured and remanufactured. You can't just be limited to the fact that it's always going to be like for like conversion. That means not everything will be convertible into the same material over and over again. Why? Because design changes, chemistry changes, structural changes. So in all of these discussions, what we are really saying is that traditional processes are not relatively easy to adapt. Maybe what we need to do is not always be bound by traditional manufacturing processes, because in some instances, you may well get better outcomes by redesigning manufacturing. So if you think about holistically, what do we have? We have input feedstock, and we have manufacturing, and then we have the actual product that we're making. Let's talk about the product itself. Product has to be fit for purpose. And of course, what that then means is all of these materials and manufacturing has to, of course, be designed with a view to preserving and protecting our planet. And this is the reason why when we talk about sustainability, it's not just about saying, well, you know what, I'm just going to make sure I don't pollute the planet. Not just a one-dimensional view around saying, well, okay, well, I'll just put in some control measures to make sure that, I'm not emitting, pollutants into my gas or into my atmosphere or into water. What I need to be able to actually challenge the notion that the entire manufacturing system, input materials, the process, and the output are all making sure that they don't cause any more harm to our planet. So in the view to achieving those big picture outcomes, what we have basically said is that from our perspective at the SMaRT Center, we need to be able to be very clear that this is never going to be a one-dimensional challenge. This is a multifaceted challenge. We need to be able to look at social, environmental, economic outcomes. And for the sake of our planet and people, we need to understand how we're going to make sure that right from the very beginning, all of these materials. So remember when I was using examples of metals like steel, for instance, I'll talk a little bit more about green steel and why it matters. All of these materials that have already been converted by reducing that ore body and converting that into metallic output and then converting that into a highly alloyed material, for instance, requires resources. And this is why, of course, what we're saying is recycling and materials transformation is really the beginning of the journey. We have to then worry about sustainability, but we have to couple that with, of course, potential opportunities where new ways of making things matter, new technologies, and of course, new products matter. How do we get there? So the work that we do in terms of green manufacturing is not just something that says, here's something we've made in the lab, and we're now going to go and deploy that in industry. What we need is that translational piece. And that iteration between what happens between our labs, between pilot and commercialization is an iterative process. And this is where our different industry partners we work with come together, whether it is the making of green steel or green ceramics. And we'll tell you a little bit more about, these two examples in a bit more detail. So when we talk about conversion of waste, often people will tell us, but, doesn't cost more energy. Are you going to use up more energy in recycling? Well, the reality is that if you're actually comparing your baseline with the way in which conventional materials are made, a simple example could be in the making of a ceramic product, you might need temperatures that are close to 1,000 degrees. What if I said to you that making green ceramics, which is what I'm going to give you an example of, requires a lot lower temperature? The processes that we have developed allow us to take in different kinds of feedstock coming predominantly from waste resources. So in the making of green ceramics, we've used waste glass and waste textiles. Now that's just the one chemistry that we're talking about. We're working towards a whole range of other chemistries that will allow us to bring in different kinds of feedstock materials. The way we use our waste textiles, of course, is the recognition that ultimately we're not talking about converting just fiber to fiber. We're not saying, well, this particular textile has to come back to the same format in the exact same way. What we are really saying is let's recognize that materials like textile waste are blends of so many different kinds of synthetic, and natural polymers. So of course, in that sense, what we are really saying is that when we look at recyclability, we're really getting right down into that micro-recycling. So we are bringing these materials back to life. We're also doing it where regional and local solutions do matter, because then you don't have to transport these materials over long distances. So you're again saving on energy there. And of course, this is why we like to think of this as distributed manufacturing. So what I'm going to kind of give you that bigger picture story is really starting to look at that waste is really not a waste if you can rethink that entire transformation question. So it's a valuable raw material, and it's a raw material, so therefore terminologies need to change in the way we look at these raw materials. If we can move away from those limitations in what conventional manufacturing should be all about, we should be looking at the challenges where we create new opportunities through innovation and partnership. And of course, if we can do that in a distributed and a localized manner, what we will start to do is we'll start to look at those economies of purpose, a very different way to think about a solution, that not everything has to always be about economies of scale. In some materials, the amount you need is going to be a lot smaller, therefore economies of purpose makes a lot of sense. What would you do with a pile of printed circuit boards? Well, one might say, well, why does it matter? We've got copper smelters. Let's send it all out to copper smelters, and we will, of course, would have solved the problem from a copper perspective. But of course, we all know that there is also a lot of valuable tin in these materials. Would you necessarily want to harvest both copper and tin in the exact same furnace? Well, you don't have to, because reasons are the temperature conditions under which you could manufacture and remanufacture these metals are quite different. So what we have shown in many of these instances is by micro-recycling, taking out selectively that tin under separate temperature conditions compared to copper can be actually quite a useful thing to do, saving on energy. Does it work? Yes, absolutely. This is the kind of work that we're doing when we refer to micro-recycling in many instances, whether it's about making metals or the earlier example of textiles being converted into different kinds of value-added materials. It's about showing that, yes, when it comes to isolating these important metals, so in this case, we've shown examples of both tin and copper. When we isolate them, we can actually also very clearly control the chemistry and, of course, the composition. So we've looked at a whole range of different kinds of e-waste, whether it's that valuable RAM card that's left behind, different kinds of parts and components. The ability to go back and control those processes can be done readily at that micro level, and hence we're calling it micro-recycling, with the goal that distributed microfactories are able to provide these solutions. Let's look what's inside, for example, batteries. A very simple format. These zinc carbon batteries, of course, as we all know, are rich sources of manganese, zinc, and so on. But yet, of course, when they are non-rechargeable, and we're calling them as disposable batteries, in many instances, of course, they might end up in landfill. Why would we put these into landfill when it is possible to recover zinc and manganese out of these batteries? So we can start to now look at where the complexity begins. Well, we know it's got these valuable elements. Well, where would you start? Would you put them in a zinc smelter? But the current zinc smelters are not designed necessarily to be able to process both zinc and manganese. Why would we not, therefore, redesign the manufacturing process? These green manufacturing solutions that we're developing with microfactories are really developing many novel techniques. In these novel techniques, we're looking at not only selectively isolating these different kinds of elements, but taking, for example, zinc out of this mixture in a form that we can then go back and produce zinc oxide, nanoparticles of zinc oxide, so that we can actually embed that value there and then. It's not about saying, well, I'm going to make, one big piece of this metal, and then I'm going to basically drop the size down to this fine level. Well, that's the traditional way in which a lot of materials are made. You make the bulk material, and then you downsize it, and you machine it, and you do all kinds of things to be able to arrive at the kinds of formats that you want. But what if you could do that control in terms of chemistry and structure and achieve those outcomes? So those are the kinds of things we're doing. You can't do that necessarily in a traditional setting. In a bulk furnace, that is a smelter, is designed to be running on economies of scale. But what if you could do economies of purpose? You could have these distributed everywhere. Again, why does it matter? Well, you only have to look at the cost of these materials. They are expensive materials, and indeed, that's what makes it economically worthwhile. So when we start to talk about economies of purpose, this is why we're doing it. We can actually control these materials. And of course, we know the list goes on and on in terms of various applications, whether it's in energy, water, different kinds of infrastructure applications. So let me pick up on, again, another one exciting example. What would you do if you had your rare earths, of course, as part of these permanent magnets that are there in your hard drives? Simple example. At the moment, of course, the question is it's not easy to be able to isolate that rare earth in this particular instance. What we are looking at is the possibility, which we've now shown, that it is feasible and it is possible to be able to isolate that neodymium, which is then these permanent magnets, from, of course, that ferrous material. So now start to open up all of these possibilities. Wherever we need these kinds of magnets, what if we could go back and harvest and separate out so many different kinds of materials, rare earth containing materials, not just in our permanent magnets, but also in our batteries, where we've seen that there is a presence, rich presence of these kinds of rare earth materials. So all of this and some of the results that we've already published has shown quite clearly that it is possible to be able to control quality of the output. So let me start to give you a little bit more of a flavor, and as I do a bit of a deep dive into what we mean and why microfactories. So like I was saying, we're developing these micro-recycling solutions in our lab, in our pilot facilities, but what we have also done in many instances is started to take these microfactories and take them out to the sites where our partners are located. So the fact that we can have these kinds of circular solutions, circular economy works when you can actually show that everyone is committed in that supply chain. What that then means is, just imagine the local government that's collecting your waste resources. So that's who manages and owns waste materials. Now that can be put back into the supply chain. We can create materials. We can have producers, designers, manufacturers making these materials, making these products. And that's exactly what we've done with our green ceramics microfactory that's running a couple hours south of Sydney in a small regional town. And you might say, a small regional town, you know, a few hours away from Sydney, would that have normally had a large-scale production factory? Probably not, but a microfactory, yes. And why? Again, doesn't matter, because we've got commitment from the local industry, we've got commitment from local governments. The idea is that indeed, our microfactory is now been taken. It's not the materials that are coming to the factory, but it's the other way around, where the microfactory is going to where the materials are. So indeed, at the landfill site, where the local council is that's the Shoalhaven City Council, we've actually shown that on their landfill site, we can actually take advantage of the fact that waste glass is available and indeed other waste resources that we need. Now come to the end users. Well, who are the end users? That's us. Whether it's us in our homes, in our hotels, just like where we're staying here, to all kinds of places. Every time refurbishment is done, renovation is done, there is an opportunity there. No matter what sector we are in, we've got an opportunity to use these resources. So indeed, in many instances in Australia, what we have shown that there is so much commitment on behalf of, and all kudos to those industry partners, local governments who want to be a part of this circular collaboration. This circular collaboration means everyone needs to show a commitment. I'm not just saying to my local government, please take away the waste because it's a problem. What I'm also saying is that I'm actually prepared to be an end user. And the only way this system can work is that when people are prepared to commit to purchasing these kinds of materials. Okay, of course, no matter where you are in the world, when you look at the amount of waste that comes out of the automotive sector. So we've done a fair bit of work on looking at glass and tire waste and plastic waste coming out of a car. Now you might say in a car, of course, steel, recyclable, absolutely goes to recycling furnaces. But what happens to a lot of these other specialty glasses, safety glasses, laminated structures, as we know, a lot of these are challenging to recycle. You don't necessarily have the traditional glass smelter who's going to be willing to accept this for obvious reasons, different chemistries. And then you look at another kind of problematic waste I mentioned earlier around waste textiles. And this is a global challenge. It's not just a challenge in Australia and some parts of the world. Indeed, in many, many parts of the world, and as you can see the numbers there, our waste textiles are ending up in landfill or being incinerated. And even worse yet, they're ending up, of course, polluting our environment, like I was saying before. We've got microfibers and so on that have ended up in our environment. So you can imagine now, we've got all of these materials that were, of course, designed and developed to serve a really important purpose. But yet here we are. The pollution that these can cause can be very difficult to control if we don't have manufacturing strategies. So what does that look like? What have we actually done? And here are some examples. I want to take you right to where the output, like I was saying, who are the end users? These are the end users. Look at the applications from these various floor tiles to walling applications. All of this has been designed, produced in our microfactory, and indeed, the kinds of properties that we need, whether they are strength properties, anti-slip properties, and a whole range of other properties that we're working towards. These properties are going to be absolutely essential. From the point of view of an end user, this is exactly what we need to see. We need to be able to show that this fulfills the kinds of engineering properties that are required. So these are all examples of our collaborators and our industry partners. And indeed, of course, you can sort of start to dig a little bit deeper into what we're using. Yes, there's a combination of synthetics like polyesters in here. There's cotton, of course. And you can see that the polymer, which is basically textiles, is not just, in there with the colors and the aesthetics. There's also, of course, as you can imagine, important functions that these polymeric, particularly the synthetic polymers, do. So from our perspective, of course, as I said before, the partnership and our industry partner, in this case, Kandui Technologies, located in Nowra, a couple hours south of Sydney, has now set up this microfactory. And of course, access to all of these feedstock materials matters. So you can see in all of these cases, the work continues in terms of developing new solutions so we can continue to build on the portfolio of properties. These scientific and engineering outcomes matter. The first one that we have done with the glass and textile combination is what we are referring to as our green ceramic products. And this was, of course, our very first microfactory in a little small town that I can tell you not too many people in Australia have heard of, in New South Wales, called Cootamundra. And we were, of course, really grateful that we had government funding, our state government funding through the physical sciences funding, because that was that critical step, taking it out of the labs and taking it into a tiny little town called Cootamundra with literally equipment that had been used before. We had very little funding to be able to actually set up a microfactory with our industry partner. And of course, that happened a few years ago. So we've now got this microfactory up and running in Nowra that I was talking to you about. That microfactory in Nowra does indeed, have that scaled up solution. It's modular in nature, so we can certainly add more modules. So what we are really saying, to reflect on what it means to do recycling and manufacturing, is that we want to start to look at how circular economy actually works in practice. The fact that you might have different kinds of glass coming from your buildings to your cars, you can't just assume that a local glass smelter is going to basically take all of that, because your domestic glass, very different to, of course, in chemistry, to a lot of the other glasses like safety glass, which is laminated in structure. So what we are really saying here is the opportunity to create exciting new products and, of course, new jobs. So The difference in terms of the two opportunities here, one is the traditional conventional supply chain when we look at materials coming in, products being made, and of course these then being disposed of at the end of its life. On the other hand, if we were looking at circular supply chains, now we start to make life a little bit more interesting. Because of course, this is where circular economy can fit in quite nicely. If you wanted to repair parts and components, in the repairability, the critical element that you need are all the feedstock materials. If you could access your plastic filaments to metallic powders to ceramic powders, you could actually start to 3D print different kinds of parts and components. So the critical thing in all of this is, yes, we do have access to technologies like 3D printing. The important thing, of course, when we start to design and redesign our parts and components, we start to repair, we're suddenly now expanding the notion of the fact that circular economy has got to be always about making something from a blank piece of paper. Why would we not look at putting in new components and parts if we could possibly do that? And this is where, of course, the thinking of how we achieve high quality feedstock is going to be an important part of connecting to the end manufacturer. The end manufacturer who might want a particular component or part repaired will need to be given assurances that, of course, the quality of feedstock material is going to be fit for purpose. And this is why, of course, when we talk about renewing and remaking, it's all about saying that ultimately the ability to bring materials back to life over and over again, that whole green manufacturing piece actually relies on the fact that we can go back and source different kinds of materials. And they are right here, part of our existing activities in our buildings, in our homes, in our electronic systems. So this is what our waste to products through microfactories looks like. It's about ultimately creating those green materials. You don't have to be somebody who runs a full-fledged microfactory. We've also got basically businesses that are harvesting waste textiles, for instance, Textile Recyclers Australia or Kandui. All of these are industry partners who can play a part in the supply chain. Of course, with Kandui Technologies, running a microfactory means that you can create these green ceramic products. So of course, when we first started out, all of this at UNSW, this is what we have in Sydney. These kinds of smart microfactories, as I said, they are modular. We want to be able to make sure that every module is there testing right down to the fine-tuned detail. So you'll see on the back side on that TV monitor, what we're looking at is what happens to, for example, those printed circuit boards that I was showing you under different controlled conditions of temperature. What kind of alloys could you produce and what's the quality of that alloy? Why all of this matters is because what we are doing is we're minimizing transport as much as possible. We're converting that waste into value, and by doing so, of course, what we are doing is lowering the carbon footprint. We want to be able to create those materials and produce things in the region so that we can actually create those decentralized solutions and create local jobs. So the whole vision for SMaRT Center has been very much about understanding and pioneering some of these pathways, these techniques, all the way down from a micro level. How would you, for example, create those smaller particles, whether they are microparticles, nanoparticles, or indeed a whole range of other materials that are needed? How would you go about doing that if you've got a complex mixture to begin with? So the important techniques, what we have designed and developed, are each of these steps along the way. And indeed, the example that I want to take you through in a little bit more detail is our own green steel example that we've now commercialized. And this example is showing, again, the same kinds of principles. What do we mean by micro-recycling that I was referring to earlier? The whole point about looking at waste as a valuable resource in the making of green steel is that what we are saying is that complex molecules that are present in materials like tires, for instance, can actually be appropriately transformed, and they can be part of the kinds of reactions that take place, for instance, in this case, in the making of steel. what do we need in the making of green steel? We need, of course, hydrogen molecules so that the reduction reaction can be carried out using hydrogen. So, of course, the reason why we've gone after products like tires is they are, of course, a source of hydrogen. But the question is, are we able to unlock and liberate those molecules in a way that makes sense from the user's perspective? So if I'm somebody who's making steel, I need to be able to liberate those hydrogen molecules at the right speed, in the right format. It can't be a two-speed race where, hydrogen's doing its own thing and not actually participating in the reaction that is required, the reaction of conversion of metal oxides, in this case iron oxide, into iron, and then, of course, all the other associated reactions that we need to have. So these are the kinds of things that we are doing. We're looking at the kinds of opportunities that we have for industry. And of course, one might say, well, what's the problem? Tires. Well, of course, the problem is that everywhere in the world, we've got massive challenges in terms of stockpiles of tires. And they can be, of course, risky if they catch fires, we know very well. So the goal for us very much was, and I'll explain this reaction in a minute, but what we are doing is we are injecting these kinds of polymeric materials. These kinds of polymeric materials, as you can see from that chemical reaction that is taking place, that video is actually shot by looking inside a furnace. And that liquid slag that's bubbling away, the reason why you see those kinds of bubbles is because of that liberation of gas molecules, hydrogen, that then participates in the reduction reaction. And that liquid slag is basically, that contains iron oxide, and of course, could be varying slag chemistries depending on the furnace itself. You can see, of course, the kinds of steel products that are being made. We have, of course, done this work in partnership with industry in Australia to show that, yes, indeed, we can replace, through polymer injection technology, a significant amount of traditional coal and coke that would have normally been used. So now the question is, well, what happens to those product molecules? So when H2O is reacted with iron oxide, what you're really getting is indeed the product, the byproduct there, which of course, the product of that reaction itself that allows us to liberate and unlock the metallic product, which in this case is iron, of course also liberates H2O. Can we now imagine a situation where inside that liquid slag, think of that liquid slag as effectively that mini reactor inside your furnace? Can we keep regenerating that hydrogen back in? To be able to do that, of course, we also need some amount of solid carbon. And that's exactly why we've shown that our micro loops work, because we can keep regenerating inside that liquid slag. And of course, in doing so, we're relying predominantly on hydrogen to be able to carry out that reduction reaction. So when we talk about these processes, what we are really saying is recognizing that it's not just about saying that tires contain hydrogen and carbon, but it's also about saying, well, at what speed, under what conditions would we be able to liberate these molecules? And indeed, how would those reactions take place? Are they going to be as efficient as traditional coal and coke-based materials? And of course, those are the kinds of questions that, rightfully an end user, a steel-making partner would ask. Is it going to be as efficient? Yes, it's great to be able to make green steel in this way. So what we had to go back and do is start to redefine when we're saying that we are talking about these 3 R's of reduce, reuse, recycle. We're going beyond that and we're saying we're reforming the structure to liberate these hydrogen molecules and carbon. And I'll explain to you why indeed this is actually shown to be more efficient in just a moment. But again, the benefits and the reasons, as I said before, is that it is about using and taking advantage of both hydrogen and oxygen that is present in the molecular structure. Now, of course, industries that contribute significantly, and there are many of them, steel is indeed one of them, to carbon footprint. And so by taking advantage of these kinds of waste materials, what we are doing is delivering a win-win outcome, both for indeed the steel industry itself, but also for the waste sector. So how do we achieve that goal? what you can see there, that injection lance that's going into the furnace in that slag layer is feeding in those rubber particles. That then allows the chemical reaction to take place inside that slag layer. As soon as iron is formed, as a result of that reduction reaction, what you can see, of course, is that that metal bath at the bottom is where the reservoir of metal is collected. So ultimately, the goal for this type of liquid slag that sits on the surface is to not only, of course, act as a great way to bring in raw materials, to bring about that reaction, but traditionally, in this type of electric arc furnace, we have to also maintain slag foam. So if you recall what I was showing in that earlier reaction, where the bubbling reactions was taking place, we had effectively a foam. Just picture your foam on your cappuccino. That foam is what we have on the surface of metal. Why does that matter? Because what it's allowing you to do is effectively act as the medium and as an insulating medium, allowing that arc from that graphite electrode to be directed straight down towards where the energy is needed. If you don't have that slag form, what ends up happening is there's a lot of radiation losses where indeed that energy is directed towards the walls and you're losing a lot of energy. So the idea in preserving that kind of foaming capability is important. I'll show you a few images as to how these materials can actually behave quite differently in the way that foaming reaction takes place. So, just to give you a bit of a sense of, in case you're wondering, is the world going to run out of rubber tires because we're now starting to make green steel? Well, I can assure you there's plenty of other stuff that we as human beings use. One of my all-time favorites, you heard me use the cappuccino example, as you can probably gather, is I love my coffee. So yes, indeed, with coffee as well, we've got an opportunity to harvest hydrogen as well as carbon. And you can see what's exciting in all of these cases is that indeed, a lot of the traditional resources, like coal-based resources, they don't have as much hydrogen. If you look down that hydrogen column, you can see, of course, that rubber tires are around 8%, but indeed coffee also has about 6% hydrogen. So the ability to harvest that hydrogen and indeed that solid carbon that we were talking about earlier is critical. So let me give you an example, just one city. And again, one might say, well, but do we have enough coffee in the world? Let's put it this way. Between tires, coffee, and a whole range of other materials, our planet actually does quite well. That's us. We do quite well in generating a whole lot of waste. Except if it became a raw material, it would really allow us to harvest them in a positive way. But here are just examples of the fact that, even in Sydney City's example, that we have significant amount of waste coffee that is available to us. So just as a quick sort of overview of why these results have been so successful, you can see, of course, the reactions and the degree of reduction that I was talking about earlier. That comparison there, that green line is with coffee, obviously a lot more efficient compared to, indeed, the metallurgical coke itself. So you can start to see, of course, and a lot of this, if anyone's interested, a lot of that detail has already been published, but you can start to see, of course, that not only from the presence of course, the fact that it's got hydrogen, the results are showing that this clearly has an impact on the reaction, which, of course, as we said earlier, is attributed to the presence of hydrogen. Again, here you can start to see the results quite clearly in these two cases. We've got iron ore, that's hematite, with coke in that blue, and iron ore with coffee waste that, of course, shows under similar conditions far more efficient reaction. So indeed, what we are starting to see is that waste really shouldn't be counted and be written off as if it is a waste material and therefore it's a problem. maybe what we need to start to do is literally look at it a little bit more deeper and indeed start to see the opportunities that it has to offer. So a little bit more of what we have done in terms of the actual use of these materials in the making of iron and steel. You can start to see here a lot of the work that has been published shows that it's not just about the reduction of iron oxide. We can also dissolve carbon in the metal, the parent metal. So in this particular instance, you can see that the carbon content of the metal has indeed reached the kinds of levels that we might be looking for in this instance. So also that carbon dissolution reaction that we have shown to be successfully achieved, again, demonstrating that the solid carbon that would have typically come from coal and coke, of course, in this instance, is more than capable of being provided by coffee. I'm going to just skip a couple of this detail here, but really just to be able to show that if anyone's interested to track through the mechanisms, the reaction mechanisms of how indeed with rubber we've been able to liberate both, as I said, hydrogen molecules as well as, of course, carbon itself, and the stepwise process of reduction as well as the micro loops means we're able to keep regenerating that hydrogen and continue to have that reduction reaction, like I said. So in the interest of time, I'll just give you a little bit of that summary with different kinds of polymers. You can see the size of those liquid slag. In all of those cases, the reason why you can see, of course, the size of that foam is different because the level of hydrogen that I was referring to, the kinds of reactions and the system that has been set up is quite different depending on the polymer. Remember that top row that you're seeing there? That top row is with the traditional material that's 100% coke. And now we've got all these other polymer materials that are showing better performance compared to the level of slag forming that we could see in the top row. And those are the kinds of benefits and advantages from an operational point of view, from a chemistry point of view as well. So I've explained to you a lot of that detail as to how it works in these electric arc furnaces. So I'm going to just skip through that. A lot of that fine-tuned detail that we start to demonstrate in a confocal microscope here at 1550 degrees Celsius of how these small molecules are present inside liquid slag. So that SBR, that's a rubber, and of course liquid slag, you can see the phase and the embedded gas molecules inside it. That's what allows us to create the kinds of foamy structures that I was talking about, and giving us that kind of stability in our foam is absolutely critical. So a whole range of developments taking place in the steel industry, and I'm just going to skip through all of that. Apologies, I didn't get a chance to come through in talking about some of the elements in batteries as well. As I promised, we're also looking at a whole range of materials coming out of batteries and regenerating these metallic outputs. So I want to just reflect there and pause that the kinds of green materials that we're talking about is really coming about because we're starting to think about going beyond the 3 R's of reduce, reuse, recycle. What we are talking about, that 4th R of reform, it is absolutely critical that we bring that innovative thinking around sustainability so that we can create these value-added materials. They have to be fit for purpose. They've got to be developed for the sake of our people and our planet. Thank you very much. Thank you.
Question? We have time for one or two. Judith.
I mean, you talked about recycling glass, and of course, it's a pretty benign material, and you put that in the ground, it's not terrible, and the energy it's going to take to recycle it, is it really worth it?
Yeah, so Judith, I'm glad you asked that question, because what happens is that you have to compare with what is the product you're making in the first place. So if you can imagine the kinds of temperatures and transportation that's involved in moving heavy ceramic materials around different places, what we are really saying is that the kinds of glass-based products that we're making, we're not smelting glass. So this is solid-state glass that is actually being bonded together with the use of that polymer. The temperatures are much, much lower compared to traditional glass smelting processes. And that's why I was sort of saying that, in many instances, you actually almost have to question whether you need to smelt in a traditional setting. So being able to minimize transport by taking, this is exactly why I gave that example of that city, Nowra, a few hours away from Sydney, is that we don't have a glass smelter anywhere in that area. But what we do have now is a microfactory that can produce these kinds of green ceramic tiles. So that's exactly why, from an energy point of view, it's a lot more efficient compared to smelting.
Thank you.
Yeah?
Thank you, EVeena, for a lovely talk. The earth scientists are saying that we're going to run out of copper. Do you think that your recycling process will solve that problem?
Thank you, Andrew. That's such a good question, because I think you're absolutely spot on. I mean, this is where I think we've got to be very mindful that when we start to talk about electrification, important metals like copper, what is our long-term strategy to be able to make sure that we've got access to metals like copper? I mean, if you, of course, can look at the amount of copper that's already embedded in our systems and our devices all over the world, you know, it's not about saying, let's just set up one big grand smelter and let's just chuck everything in there, because where would you set up the big grand smelter? But what if instead go back and have these decentralized systems, which is why, of course, we're developing this so nothing actually is thrown away. At the moment, if you look at how much of very simple electrical equipment and just electronic devices and stuff that get thrown away because, of course, it's far too expensive to move products around, even though they do contain important metals like copper. So absolutely, the goal should be very much about, you know, being very strategic and planning for the future. That if we're going to promote more and more electrification in a decentralized manner, we need to be able to have access to those important metals. So you're absolutely right, Andrew, in that we've got a plan as to how we're going to support those local economies, bringing in a lot of these kinds of end-of-life, obsolete devices and systems that are, you know, obsolete. Yes, designs move on, but sadly, if a lot of that simply gets used in an inefficient manner, or worse yet, doesn't get used at all, it's an opportunity for the world to be able to go back and harvest metals like copper and tin and so on for our future.
Thank you.
Thank you. Thanks. Thank you.